Hello, everybody. Hey, we are going to be talking about circular motion and circular or acceleration in the circular direction. Now, so far we've talked about acceleration in terms of straight lines. For example, we know that acceleration is equal to the change in velocity over the change in time, which has led to for example, our second kinematic equation, which would be B final is equal to B initial plus AT. Now, I would like to remind you that velocity is a vector component. So if you are, and a vector is going to have a direction. So if you turn, you are changing your direction, even if your speed stays the same. And if you change the direction, you have to have an acceleration. Okay, and that's really where we're going to, this lecture is about, at least the first part of it. So we're talking about centripetal acceleration. And what I would like to show you is kind of the logic and the derivation of our formula for centripetal acceleration. So what I've drawn over here is a circle, and I've tried to make it nice and precise, but it really doesn't have to be. The logic is just going to go around. If you have an object that is moving around, okay, and I'm going to say an object with a constant speed, right? So if it's going at the constant speed, let's say 10 meters per second, something like this, it's not a constant velocity because it's constantly changing directions. Okay, but if we can say the constant speed. So as we're going around here, we're going to kind of set up two little spots here. So this right here, we could think of as the constant speed. So this is going to be the initial velocity, and this is going to be the final velocity. And by putting absolute values around it, we can think of it as speed, because it's going to be going the same speed. So we're going to talk about uniform circular motion. So same speed all the way around. But again, it's going to end up having an acceleration. So here is that. So if we have a triangle, it's going to go a certain distance, okay? And we're going to look here, and we're going to draw a line across here. Go. So from a vector point of view, this right here is going to be the change in R. So this would be R initial, and this would be R final. So that right there is going to be the change in R. And from the lecture, week 2, lecture 3, I think it talks about when you're subtracting vectors, okay, it would really be the final minus the initial. But when you set that up, it's going to end up being this vector right there. So that right there is our change in R. Now, as you probably also know, that the velocity of an object going around in a circle at an instant, okay, it is going to be tangent. It is going to be tangent to that circle. So what we have here is we are going to have 90 degrees, and right there we would have 90 degrees. And remember, we can pick up these vectors. And I'm just going to call these velocities, even though they're the absolute velocities, okay, they're speed. And we want to know what is this angle, okay? And I am going to call that angle beta, okay? And we don't know what that is, okay? But what we do know is that we have an isosceles triangle here, because this R and this R is the radius of a circle. So those R's are going to be the same. And if we end up having, for example, the delta R, okay, this with respect to this, delta R is to R, and what we are searching for is to make this equal to delta v, right? So if this is our initial velocity and that is our final velocity, this would be our delta v. And so what we're trying to get here is delta v over v. Okay, and again, these two are the same from an absolute value point of view because they're going at a constant speed. So really here, if we can prove that beta is equal to theta, okay, then we have similar triangles, and we can go side with respect, or the end with respect to the side would be proportional to the end with respect to the side, okay? And that's what we're going to look for. So if this is theta, right, then this angle right in here is going to be phi, right? So we can set up here, and I'm going to do it right over here. We can say theta plus 2 phi would equal 180 degrees, because the sum of the interior angles of any triangle is on a plane is going to be 180 degrees. Okay, so now what I'd like to do is to talk about this angle right here, and I'm going to call that angle alpha. I'm going to talk about this angle being alpha. So now what we're going to say here is that alpha plus phi is going to equal to 90 degrees, because that's tangent. It's going to form a 90 degrees. So this angle plus that angle is going to equal to 90. And now what I'm going to do is I'm going to multiply this by 2, and I'm going to get 180 degrees. And since they're both equal to 180 degrees, we can say theta is equal to 2 phi. Sorry, theta plus 2 phi is equal to 2 alpha plus 2 phi, and then this side will cancel out. So we know that theta is equal to 2 alpha. Okay, and remember that we can pick up this angle right here and put it there, and we can pick up this one and put it there. Okay, and we can see if I take this and bisect it, we can see that this angle right there, okay, is going to be alpha, okay? And what's perhaps harder to see is that we can have alternate interior angles here. So this would be phi, but then this would be alpha. So that would be alpha. And we can now say that this alpha and this alpha, okay, 2 alpha would equal this angle right here, which was beta. And beta is equal to 2 alpha, but 2 alpha is equal to theta. So now what we can say here is that beta is equal to theta. And now we end up having this triangle right there is proportional, okay? Because we have similar triangles. We can have side angle side, side angle side. We can prove that they're congruent, which is kind of what we just did there. Now, because they are congruent, okay, what we can say here is that the end, which I have down here, we can say delta v over v is equal to delta r over r. All right. The end is proportional to the side as the end is proportional to the side. Okay. And now what I'm going to do is I'm going to multiply v times both sides. And that means it's going to cancel out there. So I'm going to have delta v is equal to delta r v over r. And now I'm going to divide by t. I'm going to divide by t. Now, as long as I divide both sides, algebraically, we are good. So now we've got a couple things. Change in velocity over the change in time is equal to acceleration. Okay, and change in r over change in t is equal to velocity. And velocity times velocity is equal to velocity squared. And velocity squared over r is equal to our acceleration. Now that acceleration is what we call centripetal. What we call there is centripetal acceleration. Okay, so in order for a particle like this rubber stopper on the end of the string, as we go around, there's got to be some sort of acceleration that's pulling it towards the center. And that is going to be the rope is constantly pulling it, which is going to be centripetal force. And we're going to talk about forces in the next unit. But it's always going towards the center. So we call this centripetal acceleration. Now, also in your book, because when we start in the middle, we usually call that 0 and we go outward, okay? We talk about radial acceleration, and radial acceleration is just equal to centripetal acceleration. So that acceleration is always towards the center, but when we talk about radial, we're just really talking about changing the sign so that it goes from the middle to the out is going to be positive because it's going out that way. So it's going to be going this way. So this right here is the centripetal acceleration. All right, and that is kind of the first equation that we are going to talk about. And now, if we have something that is going in a circle, okay, then oftentimes we're going to talk about the period. So we're going to have velocity is equal to distance divided by time. And in this, we're really talking about speed, okay, which is going to be the absolute value of that. And if we talk about the distance all the way around in a circle, that is going to equal to 2 pi r. And how long does it take? It takes 1 period. So this capital T stands for period, and it is equal to the time. It is equal to the time it takes for one revolution. So we could say T is equal to 2 pi r over v, okay? And which would be the speed, with that absolute value, it's going to give us the speed. And that is all for this lecture on centripetal acceleration. And we will have questions on that starting on Tuesday. All right, take care.